Okay, right here is our circular motion. When we say circular motion, what do we imply? When an object moves around a circular path, any circular path, anything circle, once it completes a 360 or just move in a circular way or a circular path, it is said to have a circular motion. So an example of all this we are talking about, an example of this circular motion is when a stone is tied to a string and it is whirled around horizontally or vertically. So number one example, let me write, is when a stone tied to a string and whirled around in a vertical or horizontal path. Okay, when the stone is whirled around horizontally or vertically. And this is our second example of circular motion is when the earth moves around the sun. It is making a circle, it is still a circular motion. The earth around the sun, the earth moving around the sun. The earth moving around the sun. And the example is the planet also. The planet revolves, it moves around the sun. Again, our three is planet moving around the sun. Then another one, the moon moving around the earth. Let me say this is number 4. The moon moving around the earth. Then another one is also the satellite moving around the earth again. The satellite. The satellite moving around the earth. The satellite moving around the earth. So now, all these are examples of circular motion. Let's go over and discuss. Let's use from this our number 1 example and get a nice concept of this circular motion. Let me wipe the board. This is our string and this is our stone. Do you get? When this stone is being whirled around, so this stone will be moving from all these points, from here to here. This will be the movement of the stone, and also from here to here. And this place is the center of the circle. So when you have a stone like this, it will be rotating. Do you get? And eventually, as you are whirling this stone around, as you are moving this stone around, if the stone cuts, if it cuts off, the stone will move away in such a way that is tangential. The stone will fall out like this, in such a path that is tangential to this circle. This now will be our stone. This is where the stone was, and this is our velocity. It will move away in such a way that it is tangential to the circle it is making. Do you get? And this is our velocity. Again, we notice as it is moving around, it is moving with a constant speed. When you are moving around a circular object, you are said to have a constant speed. But if you check something, the direction is changing. And when the direction is changing as you are moving, therefore, there is a velocity there, because velocity is displacement over time, which is displacement is direction in a specified distance in a specified direction. So the velocity is also changing because it is in a circular path. That brings about what we call acceleration. We know that acceleration is change in displacement over time, or the rates of change of displacement. So there is acceleration. So if you move from here to here now, once the velocity is changing, we have acceleration, and this acceleration is known as centripetal acceleration. This is our acceleration, and the acceleration is acting inwards to the circle. And our acceleration, here is our acceleration, which is v squared all over r. And this acceleration is acting inward. Okay, and we know from our formula that force is equals to mass times acceleration. Do you get? Mass times acceleration. the force holding this spring, this stone from falling out, let me say this marker now, the force holding this marker to be moving in a circular form is this my hand. This my hand is the force that is responsible for not allowing this marker to fall out. So there's a force here. This force is the force holding this circle from doing what? Falling out. And this force is acting inward to this circle again. And this force is acting inward. Thereby, this force is what we call centripetal force of acceleration. This force is our centripetal force. This is our centripetal force. And this is our mass. And this is our centripetal acceleration. And thereby, our force will be mass. Our A, here is our A, which is V squared over R. Therefore, this will be mv squared all over R. This V is the velocity. This is the velocity. This is the radius. And this is the mass of the stone. And this is the mass of this stone. Okay? So from here, we can, from this formula, just keep note of this formula. When we start calculation, we'll do a lot of calculation using this formula. Okay? And again, if you go over to third law of Newton, Newton force of Newton, it says that in every action, there is equal and opposite reaction. Once there is up, there must be down. Once there is F, there must be once there is heaven, there must be earth. Once there is yes, there must be no. So in every action, there is equal what? Reaction. Do you get? Okay. When there is a force moving inward, there's supposed to be a force moving outwards. And this force moving outward is what we call our centrifugal force. So there's an inward force acting here. Inward force acting here. There must also be an outward force, which is our centrifugal force. Okay? Now let's go and discuss about this our centrifugal force in detail. Let's know the examples and the application of this our centrifugal force. Okay. Over here is our examples and application of centrifugal force. And our number one example is the motion of a car around a bend. The motion of a car around a bend. When you are inside a car at a bend, if the car turns, let me say if the car is trying to go around that bend, there must be a shift inward from you to balance what? The tug or the force of the car so that you will not fall. And number two is the motion of a cyclist around a bend. If a cyclist now, or if you notice cyclists when they are on top of their bike, when they want to go around a bend, the cyclist himself will bend before the bike bends. Do you get? And when the cyclist bends, his weight plus its reaction, the weight is the downward force plus the reaction, forms a couple. And this couple balances the tug that the force creates. When he bends like this, he will form a couple that will balance with the force. Therefore, he will not fall. But if the guy is like this, there must be a tug that the force will create, that the bike will create, and there is no couple to balance it, then the guy will fall. If you're like this, round the bend, you will fall out. Okay? Number three is vehicle round a curved track. A vehicle round a curved track. If a vehicle is moving now round a curved track, the frictional force between the tire and the road will enable it, when there is a great frictional force between the tire and the tarmac road, it will enable the guy to turn around. But what if he is moving on a high speed? Therefore, he needs a great centripetal force. You get? He needs more frictional force or more centripetal force to hold him. But he's on a higher speed, then he does not have that centripetal force. He will just skid away from the round track. Okay, right over here is our applications. And the number one application of this centrifugal force is the use of centrifuge to separate particles from liquid in which they are suspended, or to separate two liquids of slightly different densities, e.g. cream and a milk. This is number one application of centrifugal force. Number two is in dryer, the centrifugal dryer, to separate water and the wet clothes. These are dryers that we use to wash clothes in our house. It is the application of this centrifugal force that dries our clothes. It separates the water from our clothes. Do you get? And number three here is in the medical field, to separate various solid constituents of blood which have different mass density. Okay, let's go over to angular velocity now. When a car, let me say this is a circle, and this is the center of a circle. Do you get? Let me say this is our radius. Let's say this is a radius now. This is our radius. If a circle is rotating, it is said to have angular velocity. Let me say, if this circle now is rotating like this, it is said to have an angular velocity, which is noted with W. Okay? And what if this circle, let me say, there was a point here, this is a stone, and it rotates to here, and this is our radius, and it makes an angle of theta. Do you get? Therefore, our angular velocity is said to be, this distance, this theta, the angle it makes during its rotation with the time it takes to make that angle. That is, it will be the angle it makes while rotating with time. That is, and it has a unit of rad per second. It's radian per second. So angular velocity is just the rate by which this our angle changes. Okay, and again, if we check from our former solving, we know that velocity, let me say, we know that velocity is equal to displacement, which is s over time. This is our velocity, displacement over time. And if we come here, this is our theta. If we check this theta now, is an act of this rotation. This theta is the total distance of here to here plus our radius. This theta is gotten, okay? This theta is gotten from when this radius, this line of radius, goes a distance of here to here, and this distance is what we denote by s. This theta is gotten when this radius goes a distance from here to here. Therefore, our theta now will be equals to this distance, which is s over radius. This is our theta. So from here, we can simply go ahead and make our distance or displacement the subject of the formula, and our displacement says that s now is equal to our theta times our radius. This is now our displacement. If we substitute this our distance or displacement here, we will now finally get that our v is now equal to, this is now theta over r all over our time. Okay, but if we check theta over time, from here is our angular velocity. We have theta over time. If we remove this theta over time and put our angular velocity, then our v now will be our angular velocity multiplied by our radius. This is our velocity. So let's now go over and solve some questions using this angular velocity. Here is our number one example, which said that a mass of 20 kg is moving in a circular path of radius 4 meters with a uniform speed of 60 meters per second. Find, our number one is angular velocity, number two is centripetal acceleration, number three is centripetal force. So let's start by writing our solution. Let's bring out our given data. Okay, it says a mass of 20 kg. This is our mass, 20 kg. Moving in a circular path of radius 4 meters. That is, our radius is equal to 4 meters. With a uniform speed, our v, linear velocity, is equal to what? 60 meters per second. Okay? Let's from this go over here and get our number one, which is angular velocity. And angular velocity, our angular velocity is W, which is equal to our theta over time. This is our angular velocity. But if we check, because I don't know which formula, we have many formulas, I don't know which formula to use. But if we check, this is our theta, this is our time, but we don't have theta here and we don't have time. So we check another formula that we have for angular velocity. And we know that velocity v is equal to r times angular velocity. We can from here make our angular velocity subject of formula which says that angular velocity is equal to our velocity all over r. Do you get? So we have two formulas now for velocity, we don't know which one to use, but our given data can help us to get which formulas to use. This one has velocity and radius. This is our radius and velocity. So this is the formula we're going to use for this one, which says that velocity, which is 60 over what? Velocity over radius, which is 4. 60 over 4, and therefore this will give us 60 divided by 4 will give us 15 rad. 15 rad per second. Okay, and this is the unit for our angular velocity. And the second says we should find centripetal force, centripetal acceleration. So let me leave our given data. Let me wipe here. Let me wipe here and solve it up here. Centripetal acceleration. We know that our centripetal acceleration is A is equal to V squared all over R. And our A now is equal to, do we have V? We have velocity here, which is 60 squared all over, our radius is 4. Our radius is 4. So finally, our acceleration will be, let me punch in my calculator. Our acceleration now will be 60 squared divided by 4. It will now give us 900 meter per second. This is our acceleration. Next is our centripetal force. Let's now wipe our centripetal force. Okay, let me wipe here. Our centripetal force, which is our F, is equal to mass times acceleration. As we know, do we have mass? Yeah, we have a mass of 20 kg. Do we have acceleration? We have acceleration of 900 meter per second squared. So that our force now will be equal to our mass, which is 20, multiplied by our acceleration, which is 900. Therefore, our Ft now will be equal to, this will give us 18,000 Newton, or you can equally say that this will be equal to, that is 8 kilonewton, 18 kilonewton. Okay? Right over here is our second question, which says a stone wheeled at an end of a rope 60 centimeter long makes 10 complete revolutions in 4 seconds. Find. Number 1 is angular velocity. Our IIR is linear speed. IIR is distance covered. Okay? And we know from here, let's start. This is our solution. Let's bring out our given data. Okay. A rope. They said at the end of a rope, and at this end of a rope is our radius. Our R is equal to 60 centimeter, and next is revolution, which is our theta. It makes 10 complete revolution. 10 complete revolution, and 1 revolution is equal to 360. 1 revolution is 360. That means 10 revolutions will be 360 times 10, and 360 in radians is 2 pi. 360, or we call it 2 pi. 360 and 2 pi is the same thing times 10 revolution. So here our theta now will be equals to 2 pi times 10, which will give us our 20 pi radians per, our 20 pi, sorry, not radians, doesn't have any dimension. Okay, so let's go over and solve for our angular velocity. Okay, 2 pi rad, yes, this is our rad, not radian per second. Okay, this is our theta. Okay, our angular velocity says that W is equal to theta over time. Do you get? And our theta, you can use this formula because we have theta and time. We have theta, sorry, I didn't bring out our time. This is our time, which is 4 seconds. Okay, and our theta now is equal to 20 pi all over our time, which is 4 seconds. 4, and we should go over and solve. 20 divided by 4, this will give us 5 pi. Okay, and this can also be equal to, let me press my calculator. 5 pi will be, okay, 5 pi will be 15.7. This is now 15.7 rad per second. This is our answer. Okay, let me write our answer here out. It's 15.7 rad per second. Okay, now next is our linear speed. Our linear speed, which is V, is equal to, we know that our V is radius times angular radius times angular velocity. So from here, we know that our angular velocity is there. So our linear speed will just be our radius. Where is our radius? 60 centimeter, 60 cm times our angular velocity, which is 15.7. 15.7 rad per second. Okay? So if we multiply out, our V now will be equal to 60 times 15 times 60. It will give us 942.4, and this is meter per second. Centimeter, sorry. And this is centimeter per second. We have centimeter here, okay? If we convert this centimeter just in meters alone, we are going to divide our answer by 1000 to give us 0 points. Our now velocity will be, we are converting from centimeter, here is centimeter per second. We are converting from centimeter per second to meter per second. This now will give us 0.942 meter per second. This is our answer. And the third one is distance covered. So let's solve for distance covered. Okay, let's bring out our answer for velocity, which is 0.9424 meter per second. Let's go over to our distance covered, and we know that the velocity is distance over time. Velocity is distance, s over time, and making distance subject of a formula, it will be velocity times time. And from here we can bring out our velocity. This is our velocity. Distance is now 0.942424 times our time, which is 4 seconds. 4 seconds. So let's go and multiply out times 4. Our answer times 4. It now gives us 3.7. Our second will be 3 points. Our distance will be 3.7 meters approximately. Okay. This is our final example in motion. Let's quickly go over to linear motion, which we shall discuss about position, acceleration, velocity time graph. Let's just go over there and start.